Section 10-2 is entitled Simplifying Radical Expressions. Recall that a radical expression is one that has a square root sign in it. So a radical expression is simplified if no radicands have perfect square factors other than 1. Recall that the radicand is the stuff underneath the square root sign. In other words, has no perfect square factors other than 1, then the radicand cannot be divided by 4 or 9 or 16 or 25 or any other perfect square. Second rule, no radicands contain fractions. You cannot have any fractions underneath the square root sign. And last and most importantly, no radicals can appear in the denominator of a fraction. You can't have a radical in the denominator of a fraction. So here's a couple properties of square roots, the multiplication and division properties. So the square root of a times b is equal to the square root of a times the square root of b. For example, the square root of 6 is equal to the square root of 2 times the square root of 3, because 2 times 3 is 6. The square root of a divided by b is equal to the square root of a divided by the square root of b. So for example, the square root of 7/8 is equal to the square root of 7 divided by the square root of 8. Let's take a look at a couple examples of how we can simplify these expressions. So number 1, the square root of 54. First thing we want to do is factor tree this, and you probably remember this from grade school or middle school. So just break down 54 into two numbers that it multiplies to. And it doesn't matter which ones you start with. The first ones that jump into my mind are 6 and 9, and 6 can be broken down into 2 and 3, and 9 can be broken down into 3 and 3. You want to end up with prime numbers on the bottom. So that means the square root of 54 is equal to the square root of 2 times 3 times 3 times 3. Now, here's my kind of corny way of thinking about this. In the house, underneath the radical, we have a 2, a 3, a 3, and a 3. They can only come out of the house if they have a buddy. So for example, these two 3's can buddy up, and they can come out front. So they don't have to be, they buddy up and become 1, 3 out in front of the radical sign. 2 doesn't have a buddy, there's not another 3 for this buddy, so they have to stay inside the house and multiply to 6. So the simplified form of the square root of 54 is 3 times the square root of 6. Here's another example. The square root of 6 times the square root of 8. You could multiply those and do the square root of 48, or you can just factor tree each one of those. 6 is 2 and 3, 8 is 2 and 4, and 4 is 2 and 2. So that's going to give me the square root of, and I have 4 2's and a 3. And what I'm taking is only the prime numbers that are kind of at the ends of these little branches here. Okay? Using the buddy system, those guys can buddy up and come outside the house. These guys can buddy up and come outside the house. The 3 doesn't have a buddy, so he's got to stay inside. I can multiply the 2 and the 3, the 2 and the 2, and that becomes 4 square root of 3. So simplified, the square root of 6 times the square root of 8 is 4 square root of 3. Here's a bigger one, square root of 32, a squared, b to the 4th, c to the 5th. I'm going to start by factor treeing the 32, and I think of 4 and 8, 2 and 2, 2 and 4, and 2 and 2. So look at that, I have 5 2's coming off of here. Sometimes it's nice to circle them so you don't lose track of anything. And I'm going to take the time and write all of this out. So 32 is 5 2's, a squared is a times a, b to the 4th is 4 b's, and oh my, c to the 5th is 5 c's. And all of that is under the radical sign. Okay, so let's start buddying them up. Those 2 2's can become 1 2. Those 2 2's become 1 2. I don't have any other 2, so he has to stay there. There's 2 A's that become 1 A. There's a B. There's another B, and a C, and a C. Okay, and there's nobody there. And then what's left in the house is a 2 and a C. So let's clean this up out front. 2 times 2 is 4. I have one A and a B squared and a C squared and a square root of 2C. Now, there is a little bit of a funny rule regarding some of these larger square roots that you have to deal with. Actually, what we technically need to do is put absolute value bars around the A. And you're going to want to do that. Let's add some notes here. Use absolute value bars. When the exponent inside is even, the exponent inside is even, and the exponent outside is odd. And let's see what that means in this case. Going back to the original problem, I had an a squared in the radicand, so underneath the square root sign I had an a squared, and that's an even exponent. But then when I simplified, I ended up with an odd exponent on my a. That's really a to the 1, so I have to put bars around that. Let's take a look at the b's. The exponent inside here for the b's was even, but when I buddied them up and brought them out, my exponent was also even. So it had to be, if it had been odd, I would have had to do that. So here's a couple rules. So if you're doing the square root of x squared, okay, that's even inside, but when you pull it out, it's odd, so you have to put bars around it. The square root of x to the 4th, so that's 4 x's. They would buddy up and become x squared, but because it's even inside and even outside, no absolute value bars. And then if you do the square root of x to the 6th, those are going to buddy up into 3 pairs. That becomes x to the 3rd. Even inside, odd outside, you have to use bars. And the reason we do that is because the square root of a number is positive. We want it to end up being a positive number, not a negative number. Okay, let's take a look at another example here. The square root of 3a divided by 8. A couple ways you can do this. I think I'm going to do the square root of 3a divided by the square root of 8. And now the square root of 8 is a 2 and a 4 and a 2 and a 2. And I'm not going to take the time to write this all out underneath the radical sign, but I can see that these guys will buddy up, and this guy's left by himself. So this is going to be the square root of 3a over, these buddies can come out, 2 times the square root of 2. Now, that is not yet simplified, because if you remember one of our earlier rules here, the one that I said was very important, no radicals appear in the denominator of a radical. So we cannot have that square root of 2 in the denominator. To get rid of that, we're going to do something called rationalizing the denominator. I need to make this denominator a rational number. To do that, I'm going to multiply it by 1. And remember, there's a lot of different ways I can write 1. I can write 1 as 1 over 1, 2 over 2, 3 over 3. I can also write 1 as the square root of 2 over the square root of 2. Now what's going to happen on the bottom here when I multiply a square root of 2 times the square root of 2, that becomes just a plain old 2. So on the top, I can't really combine any of those and bring anybody outside. So that's going to be the square root of 6a. And then on the bottom I have a 2, and these square roots of 2, those are going to multiply to give me a plain old 2. So that's going to be over 4. And that, even though it's kind of funny looking, is my final answer. Okay? What I did here was called rationalizing the denominator. And that's what you have to do when you have a square root in the denominator. What I did was I multiplied by square root of 2 over square root of 2, which really equals 1, so I'm not changing the problem at all. Main rule, can't have a radical in the denominator. And one more example here. 7 divided by 3 minus the square root of 7. Again, I have a radical in the denominator. That's going to be a problem. But what happens, I'm going to do a little work on the side over here. What would happen if I did 3 times the square root of 7, and I multiplied that by the square root of 7, which might make sense. So when I distribute, that's going to give me a 7. But when I distribute here, that's going to give me a negative 7. That's going to give me a 3 square root of 7. So I really haven't gotten rid of it. So that's not going to work. What I have to do is multiply it by something called the conjugate. And the conjugate is the same as the denominator here, but with a different sign in the middle. And you're going to want to use this when you have something added or subtracted to or from a radical. So I'm going to multiply by 3 plus the square root of 7 over 3 plus the square root of 7. Okay? Notice the same numbers, but instead of a minus, I have a plus. And again, it's the same thing on top and bottom, so all I'm doing is multiplying by 1. On the top, I'm going to distribute. And on the bottom, I'm going to FOIL, because this really looks like a binomial. Okay? On the top, when I distribute, I'm going to get 21 plus 7 square root of 7 over, now when I FOIL on the bottom, first gives me a 9, outer gives me a positive 3 square root of 7, inner gives me a negative 3 square root of 7, and last, a negative square root of 7 times a positive square root of 7 is going to give me a negative 7. Now what do you see going on right here? Those guys are going to cancel each other out. So what I really have is 21 plus 7 square root of 7 over 9 minus 7, or 2. And that's a really funny looking answer, kind of like the ones we ran into with the quadratic formula, but that is actually simplified. A radical on top is okay, but we got rid of the radical on the bottom. So to rationalize the denominator in this case, we multiplied by the conjugate. In this case, it was 3 plus the square root of 7. And that's going to rationalize your denominator for you.